Hello, everybody, and my name is Takeshi Matsumoto, and I'm in the Kyoto University. So today I will talk about our work in collaboration with Uriel Frisch, Alexei Maribaev, Rahul Pandit, and Dipankar Roy. So yeah, it's about the decaying turbulence, and it's about how the total kinetic energy decreases as a function of time. And as explained in the Uriel's talk this morning, the problem of decay of turbulent flow has a very long history. So by free decay, usually we mean we assume there's no effect from the boundary. So let's say the turbulence develops away from the wall, and we like to understand how the energy away from the wall decreases as a function of time. So this is the total energy as a function of time. So this is the integral of the wave number over wave number of energy spectrum as a function of k. K is the wave number and t is the time. And the experimental fact told us that the time dependence of the decrease of the energy is a power law. So the question is how one can understand this power law exponent from the initial condition or boundary condition or other settings. So it has a very long history from Kalman, Hawass, Kormorov, and Proudman Reed, and Combello, Korsin, and many others. So this is the classical setting of problem of the decaying turbulence. And in theory, we almost always assume self-similarity for the energy spectrum, namely the energy spectrum depends on some characteristic velocity, u as a function of time, and we also need characteristic spatial scale, which is supposed to be in a large scale. And so dimensionally, this energy spectrum is the velocity squared times length. And here we have some function, f, and this function gives us some self-similar form, and that can be determined from the Navier-Stokes equation, obviously. So this is a basic assumption for the decaying problem. Okay, so in terms of the closure or theory or numerical simulation, we assume the following form for the energy spectrum during the decay. So the energy spectrum can be divided into two parts. They're divided by some 1 over characteristic length scale, L as a function of time. So for the low wave number, so this corresponds to the large scale. So in the large scale, we assume the energy spectrum behaves like a constant times wave number to the power n. For the larger wave number region, larger than 1 over L, we assume some constant times this epsilon is the energy dissipation rate. So we assume this constant times energy dissipation rate to the power 2/3 and wave number to the 5/3. So this is basically the Kolmogorov spectrum. And also the important assumption is that this constant A and B are constant, which doesn't depend on time. But this energy dissipation rate, epsilon, is now depends on time. And for some technical reason, this exponent n is limited from -1 to 4. It has something to do with decay of the correlation function, the 2-point velocity correlation function. So if we assume this energy spectrum function form, then we can derive in a phenomenological way how the total energy varies as a function of time, and also how the integral scale varies as a function of time. So the total energy is, again, I show you the definition. So it's energy, the velocity squared integral over all the domain, or it's an integral of the energy spectrum. And the integral length scale can be written for the isotropic case, homogeneous isotropic case. It can be calculated from the energy spectrum. Okay, so this is a classical phenomenological theory for the energy and integral length scale. So the important point is that this exponent is determined from the low wave number part of the energy spectrum. Okay, so this is the classical picture of the decay of homogeneous and isotropic turbulent flow. So I show you a numerical example of this decaying problem, but please note that in this simulation, we replace the Newtonian viscosity by so-called hyperviscosity. So now the viscous term is the second order Laplacian times some constant. We set the number of grid points of 500 cubed. So we start with this purple energy spectrum. It has k to the 2, k to the second power at the low wave number. And the initial energy spectrum decreases as a function of, get the Gaussian decrease in the large wave number part. So this is the initial condition. So, and the phases of the velocity Fourier modes are random. So we start with this energy initial condition, and so this is time 0. So the second curve I plot here is time 0.25. So this is this green one. Oh, sorry. So this purple is the initial condition. The second instance is this one, and the third is this one. And as time evolves, the spectrum decreases as time goes on, but this k to the second part is sort of preserved. So this is the time evolution of the energy spectrum. The time is from here to there. So at the end of the simulation, this form of the energy spectrum is probably similar to the one we often observe in the statistical steady state. But again, please note that this is a hyperviscous simulation. Okay, so in this case, the energy, the total energy, varies like this way. So this is a time, and this is the total energy, and this is a log-log plot. If you have power law, then you can see you should see the straight part. So for the energy, so we see some straight part in, let's say, from time 1 to 100. For the integral length scale, again, we have some straight part from, let's say, time from 1 to 100, and they are consistent with the classical phenomenological law. So this is the Combelot-Coursin argument. In this case, we put the k to the 2 initial energy spectrum. So we just put 2 here. Then we get the t to the minus 5/6 for the energy. And for the integral length scale, we have time to the 2/5. So they are consistent with the numerical data. Okay, so this is the classical results, and maybe you have seen this in textbooks. Okay, so here we like to move slowly to the modern account of the decay. So as I told you, we assume similar form for the energy spectrum during the decay. for the freely decaying turbulence. But the question is, this assumption of the self-similarity, is it always valid, or is it a way to break the self-similarity? So that is the question we like to address in this talk. And I should add, so up to now, I assume the flow is, the decaying flow is homogeneous and isotropic. But you may say, if we add an isotropy or some helical motion or helicity, then the self-similarity may be easily broken. But the answer is that an isotropy and or helicity may not be enough to break this basic assumption. So anyway, so this whether the self-similarity persists or not is our question in this talk. Okay, so yeah, in this talk, yeah, we have used a somewhat strange initial condition. So this is purely numerical and academic. So this is our initial energy spectrum. So this is the wave number. This is the energy spectrum. So it localized, the energy spectrum is localized at some wave number. And it has some width, and specifically it has Gaussian functional form. So K center is now in this figure, K center is 90. The width of the Gaussian is set to just 2 here. The phases of the velocity Fourier modes are given in a random manner. So we put this initial condition into again, the hyperviscous Navier-Stokes equation with the following hyperviscous kinematic viscosity. And we normalize the initial energy to as a unity, and we used some fancy Runge-Kutta scheme. So in this case, the evolution of the energy spectrum is something like this. So this is our initial condition. So this is time to 0. For the second instance, I showed in this way, in this figure is this one. So still some peak remains here, but for the higher wave number, we have some excitation. And for the low wave number part, which is the most interesting thing in this talk, is this one. So basically, the initial, in this kind of initial condition, the low wave number part soon develops. And so since this is a log-log plot, so this low wave number part looks rather straight. And here I just show you for the guide. So this is a k to the third slope. So this low wave number energy spectrum, it is spontaneously chosen from the hyperviscous Navier-Stokes equation, is maybe close to the k to the third. And another observation is that, let's assume this is k to the third, but for the constant prefactor, the constant seems to be dependent on time. So I write the constant as a function of time here. And probably in the later time, some intermediate part develops, but I'm not sure this k to the 0.5 is something really physical or not. But anyway, so this is observation for the localized initial energy spectrum. So for the total energy, so starting from the Gaussian localized initial condition, so the point, just look at those points. So this is a total energy as a function of time. This is a log-log coordinates. So those circles, purple circles, are numerical data. And this green line is empirical fit. As I show you in a minute, so I fit the total energy with this rather strange functional form. So as you can see, so the data looks okay. So it can be straight, but it can be somewhat not straight. Okay. So in order to examine whether the total energy decreases as a pure power law or not pure power law, maybe one way to look at is take the so-called logarithmic local slope, which is you just take the log of the total energy and take the derivative of the log of ET of the log T. So I calculate this logarithmic local slope in a stupid manner, just take the finite difference of the log. Then the data looks like this one. If the total energy varies as a pure power law, you will have a straight line for the logarithmic local slope. But here, it's not really straight. It's not really, sorry, it's not really a plateau. Yeah, if you have a pure power law for the total energy, you will see a flat, completely flat logarithmic local slope. But in this case, yeah, for the localized initial energy spectrum, the total energy, if I take the log local slope of the total energy, sorry, and it has some decreasing straight line, which is not the plateau, which is not pure power law. So I just fit this logarithmic local slope with a straight line in this log linear coordinate of the logarithmic local slope. It gives some constant. So there is some, yeah, let's say intercept is minus 1.2. The slope B is something like this. So this implies the total energy varies in this form. And yeah, it's just empirical. Then I just show you there's a theoretical result for this kind of logarithmic correction, which has been obtained for the decaying Burger's turbulence. Yeah, which was obtained by Kida in 1970s. So for the Burger's case, the total energy decreases some power law times some logarithmic correction. Yeah, if you have this Kida's decay law, the logarithmic local slope should be something like this. So this tau NL is some characteristic nonlinear timescale. Okay, so this is, yeah, this strange behavior is different from the pure power law. So it can be one form of broken self-similarity of the decay, the free decay of, yeah, in this case, it's a hyperviscous Navier-Stokes equations. Okay. So as I showed you, if we start with the localized initial energy spectrum, but this initial localized energy spectrum is basically composed of Gaussian random Fourier. And for this case, we can apply the very classical closure for the Proudman lead, and which was mentioned in the talk of Uriel this morning. So for the initial condition, we can apply the closure due to this Proudman lead. So the closure of the Proudman lead is this one. So the capital T is the transfer function. So yeah, let me start with the so-called Lin equation. So it's a equation for the energy spectrum. The time derivative of the energy spectrum is equal to the nonlinear transfer, energy transfer, and viscous term. Now we assume the evolution is the Newtonian Navier-Stokes equation. So if we apply the Brodmann-Reed closure, so this is basically the everything is Gaussian, random variable. So the odd order moment vanishes, and the fourth order moment can be expressed in terms of the second order moment. Then we have the time derivative of the transfer function can be expressed with the energy spectrum times some geometric factors. So our initial condition is localized around some case center, and in this case, then we can ignore the first term and the second term. The only non-zero contribution is coming from the third term. So this is basically the non-local contribution. And yeah, we like to understand the behavior of the energy spectrum for the wave number much smaller than Kc, K center. So then we can simplify this expression, and we arrive at the time derivative of the transfer function at time t0 is given by the k to the third power, and this k to the third gives us the k to the third energy spectrum for the short time evolution. Okay, so this is an argument for the k third spectrum, which is developed just after the just for the short time evolution for the localized energy spectrum. Okay, so yeah, let me explain the calculation a little bit in more detail. So our initial energy spectrum is localized at some wave number, K center, and we like to know the behavior for the wave number much smaller than Kc. So for this wave number K, the initial energy spectrum is basically 0, so we can ignore this term, and this term also the case. The third term, so this is the most interesting non-local contribution for the energy transfer, and let's evaluate this interval. And so basically, for the argument for the wave number in the integrand, we just put the Kc. Other than Kc, the energy spectrum is 0. So we put so K prime and K2 prime is Kc, and just, yeah, it's just a stupid substitution. And then this Q is given in this way, and just simple algebra, we arrive at this expression. So the K now is much smaller than Kc. So this term is subdominant. So the dominant contribution is this one. And we have, okay, so we have K to the second, and here we have K downstairs. So we have K to the third. All right, so this is the simple result from the simple closure. So our initial condition is a Gaussian random variable. So we can safely apply the Brodmann-Reed closure for the short time, and we arrive at the K to the third transfer function. Okay, let me go back to the time dependence of the total energy. So now I change the localized wave number. Sometimes this is 60, sometimes 120, and I change the resolution. And for this curve, I go back to the Newtonian, the normal viscosity Navier-Stokes, or the other curves are obtained with hyperviscous Navier-Stokes. The Laplacian is second order. For all the cases, I showed you the total energy as a function of time. So it's a log-log scale. So this most deviated curve is the one I calculated with the Navier-Stokes. So I then took the logarithmic local slope of the total energy, and it looks like this one. So the logarithmic local slope start to decrease, and then in this case, and then it turns up and go up slowly, and then it reaches to some constant. But in some cases, its approach to some constant is from above. In other cases, the approach is from bottom. So in this manner, the behavior in the intermediate time depends on, let's say, the Kc, the K theta, the wave number where the initial spectrum is localized. But the important observation is that all these logarithmic local slope getting close to some constant is -4/3. So -4/3 is a classical decaying exponent for the K3 initial spectrum. For the Navier-Stokes case, the deviation is quite large, but I will explain it in a minute. Okay, so I argued the behavior. We observed some strange behavior, and those constants A and B depends on Kc. The Kc is the wave number where your initial condition is localized. Maybe one question we can address is, let's take this localized wave number is much smaller than the dissipation wave number. Now, of course, this dissipation wave number depends on time, but during the time which this Kc is much smaller than the dissipation wave number, to experiment this situation, I increase the resolution and I increase the Kc, and also for the hyperviscous case, we can set 60. And for the hyperviscous case, I increased the resolution and I doubled the Kc. And it seems that for this condition, the logarithmic local slope of the total energy approaches to constant from below. And I don't say many detailed things, but let me just say, if I experiment this situation, the result is the result seems to collapse to one curve, and maybe this log correction approaching to -4/3 from below can be emerge as an intermediate asymptotics for the localized wave number is when the localized wave number is much smaller than the dissipation wave number. So that's one, there's still a speculation, but from several numerical results suggest this. Okay. Yes, in the Berger's case, the log correction was derived in a rigorous way. So that is called the Kida's decay law. And in this plot, I showed you again the logarithmic local slope for the localized hyperviscous decaying case. And then, so this black line corresponds to the Kida's decay law type functional form. In this case, the log local slope should take this one. Since the energy varies in this functional form, so this is a form of the Kita's decay law. So the parameter is now the P, Q, and tau. If I take the logarithmic local slope of this equation, we'll have this one. So I fit the data with this functional form, then we obtain the parameter values like P to the 1.2, Q equals to minus 0.92, and R is minus 3.3. Yeah, this is just empirical, but it's there's a good thing about this empirical functional form, because yeah, we are always concerned with large time asymptotics. So this form gives you some asymptotic power law exponent. So in this sense, yeah, this functional form may be better than the one previously I showed. But still, at this stage, it is just an empirical, and the fits, maybe this part is overfitting, and the asymptotic value of the fitted form is different from the. So there's some inconsistency, but still, there may be. I think there may be some interesting point. Okay, so okay, so now I come back to the Navier-Stokes case. So the Navier-Stokes case, the total energy as a function of time is very different from those curves for the hyperviscous case. And if I take the logarithmic local slope of this curve, and this looks like this one, so it doesn't have a plateau, and but this logarithmic local slope is always around -2. And actually, there's an explanation for -2. And the explanation for this -2 is rather simple. You just ignore the nonlinear term, then your Lin equation is just d by dt EKT equals minus nu times k squared times energy spectrum. And that gives you the time dependence in a stupid manner, exponential minus nu times k squared times t. And if we integrate over the wave number of that energy spectrum, then we arrive at this formula. So this formula for the k third corresponds to t to the -2, and probably this -2 can be explained in a rough sense with this relation. Okay, so now this is the final topic I like to discuss. So yeah, I told you our question is whether the set of similarity in the decay is always preserved, or is there some cases where the set of similarity is broken. So now I come to the basic question of the set of similarity. Okay, so so this is a classical case, starting with a k to the for the low wave number, but we give the k to the second power, and for the large wave number, I set the Gaussian decrease. And on your right, so this is a localized initial energy spectrum I've been talked about. And yeah, we like to check whether this decay is similar or not. Yeah, this energy spectrum as a function of time is it similar or not? So this is the scaled plot of the energy spectrum. So let me go a little bit slower mode. So the basic assumption for the energy spectrum, time-dependent energy spectrum, is given in this way. So this is U is some characteristic velocity. So L is characteristic length. And so L is, let me assume, so this L is integral scale. And this F is a self-similar function. And we like to observe this self-similar function from those numerical data. So in order to do that, from this assumption, so the self-similar function F can be given by the energy spectrum divided by total energy. Okay, so here I assume the characteristic velocity squared is proportional to the total energy. So we have a numerical data for the energy spectrum for different times, and we have the data for the total energy, and we have the data for the integral scale. So let's plot right-hand side. So for the classical setting with the k-squared energy spectrum, the initial energy spectrum looks like this one. So yeah, let's assume for the moment for the high wave number part is not really relevant with this self-similarity for the decay. Just look at the low wave number part. So in my opinion, it scales very well. It just collapsed to some master curve given by some self-similar function. Without this scaling, we have this one. With this scaling, we have this nice collapsed curve for the low wave number, at least for the low wave number part. Yeah, for the localized initial condition, the scaled curves looks like this. So when I compare these purple curves and green curves, yeah, I observe the green curves are not well collapsed in comparison to the classical setting. So in conclusion, so the localized energy spectrum, the scaled energy spectrum is somewhat scattered. So that suggests probably the self-similarity is broken for the high wave number localized initial spectrum. Okay, so this is the summary of my talk. So we studied hyperviscous Navier-Stokes we studied the decay of the hyperviscous Navier-Stokes turbulence, and specifically we studied somewhat non-standard initial energy spectrum, which is localized around some wave number and with some widths, very narrow widths, and the phases are random. And we start with this strange initial condition, then the subsequent evolution for the short time is something like this. So the constant depends on time, and the wave number dependence is k-third. And this k-third is understood with the classical Gaussian closure. And the total energy behaves as not pure power law, but with some correction. And in this talk, I fit the correction with this kind of logarithmic functional form. And this is transient, but yeah, this is transient. And for the large times, the behavior of the energy the total energy, is getting closer to the classical pure power law. And this exponent is identical to the classical phenomenological result for the k to the third decaying case. And I showed you there's some numerical data which suggests breakdown of the self-similarity. Okay, so this is the end of my talk, and thank you for your attention.
Open for discussion. So